Good evening. My name is Brian Bishop. I'm the CEO for 2 months. 2 months, I think, yesterday, of Skip Technology. We are in Central East Side, just a few blocks. I think we've had the Ray folks in our parking lot before I was attached to the company. I am here tonight to talk to you about our flow battery. So, why batteries? Why do we care about batteries? We care about batteries because in the modern environment, we produce energy at a different time than when we need energy. And whether that production is from a baseline steam-driven plant, that steam plants, when you turn them on, you leave them on, you do not turn them down, you do not turn them off, they go 24/7. How much energy do we need at 2 in the morning? Or if we have solar energy that is produced in the middle of the day, but not the early evening when most households need it. It's called curtailment when you dump that energy. Or wind, when you capture the energy when the wind blows, which could be any time, day or night. The problem we are solving is we are capturing energy and releasing it later when it is needed. In the industry, is called long duration energy storage. And unlike lithium batteries, which are really good at 2 to 4 hours, our battery is a flow battery, so it stores the energy in the chemistry and can be stored for any length of time. There's no self-discharge, no degradation. It's just there. It's in the chemistry. So that was the problem we're trying to solve. And how do we do it? We are doing it with hydrogen and bromine. Hydrogen is fairly well understood. You handle it outdoors, it vents off. Everybody's happy. Bromine is most commonly used as a fire retardant, which means it doesn't catch fire. Lithium battery, if it catches fire, it goes out when it wants to go out. Now, having said that, there's been a lot of progress on lithium batteries. Don't get me wrong. A lot of progress. I'll be fully satisfied when the airline ticket agents stop asking me if there's any lithium batteries in my bags. So how does our system work? We start with hydrogen. It's a closed system. Tank of hydrogen, tank of bromine. Goes into a reaction chamber through a laminar flow membrane. All would use polymer membranes as well. They both work. And we get energy out. And on the bromine side, we get hydrobromic acid. And that's a closed system. So the more power we pull out, more energy we pull out, the less bromine we have, the more hydrobromic acid we have. Then when we charge, we reverse the process. We put a voltage into a reaction chamber. It breaks apart the hydrobromic acid, frees off the hydrogen gas, which we can store, and that's a link. The second is that it's easy to intimately scale power and energy. So power is 100 watts. Power is I'm turning on a light bulb. Energy is how long I can run that 100-watt light bulb. 100 watt hours. You've heard the term kilowatt hour. Because of our system, we have completely decoupled, 100% decoupled power from energy. So when you have a 100-watt system and you have a kilowatt hour of energy, if you say, gosh, that's not enough, I need 2 kilowatt hours, fine, get tanks twice as big, twice the bromine, twice the hydrogen, ready to rock. 10 times more, no problem. So it's very, very similar. And because the energy is sitting in that chemistry, look at the lower right-hand corner, no degradation. That energy can sit there for days, months, years. Try doing that with any other battery. So there's no self-discharge, no degradation over time. How many people on their iPhones? They're on an iPhone. And for phones, it's talking about the lithium. Really, and there can't be. I keep my charge to 80% because Apple says to do that. And I get a lot more cycles out of this. We don't have to play those games with our technology. The other really, really cool thing about our technology is it's fully domestic. At Skip Technology, we believe the Chinese substantially erred last summer when they demonstrated to the world that they can put their boot on our throat and cut off whatever export they want to cut off. We don't have rare earths. Bromine is a byproduct of desalinization. Hydrogen's really easy to get. So we have to only worry about a gas diffusion electrode, where we have both US and European sources, and carbon plates, where we have to make our own anyway, so it will be as part of our development cycle. Something else that's very cool about our product is that it has a very wide temperature operating range. In our system, we can run up to about 60 degrees C, which is way hotter than you want to be living at. You can't do that with most other battery technologies. You have to spend a lot of parasitic power to keep that system cool as operate. Our challenge is to keep it warm at minus 10 C. Okay, we can solve that problem. That's an easy problem to solve. So that is the advantages of our solution. Competitive landscape, kind of an eye chart. There's a lot of really good technologies out there for a lot of particular purposes. And no battery should claim to be all things to all people. We serve this community scale, microgrid scale, time shift energy problem. There's a lot of people in data centers talking to us. There's a lot of people in rural superchargers talking to us. Gosh, my Tesla supercharger needs 350 kilowatts. Oh, look, the power company will only give me 100 kilowatts. But you put one of our batteries next to that supercharger, you charge up the battery at 100 kilowatts, and when someone drives up and discharges at 350, so what? So that's the problem, another problem that we can solve. Where are we at right now? In October of this year, about the time I joined the company, it's how I got roped into the company. Wasn't really forced. It's a lot of fun. We got to a consumer scale demonstration. So driving a standard commercial off-the-shelf 48 volt input, 120 volt output inverter. We were powering TVs, phone chargers, cauldrons for Halloween because it was October, that we could do that. So we were able to do that in October. Our goal this year is to get to a 2 kilowatt unattended remote prototype, 2 kilowatts, 20 kilowatt hours. And from there, we quickly scale up for the building resiliency, grid resiliency, and 100 kilowatt commercial launch in 2028. My name is Brian Bishop. I am with Skip Technology, and I'm available for your questions.
My question is, how does this compare to pumped storage hydropower, where we just, it's also another way of like storing energy where you just pump like water uphill?
Yep. Pumped storage is an interesting technology. It's for bigger scale. So it doesn't serve the resiliency need of distributed resiliency. If you have a large facility, you can do that. It works. Again, not one solution is best for everything. I think we'll find as those systems get fielded that the round trip efficiency isn't quite what we hope it would be. And there's some operational expense issues and also working a site them, but there's a limited number of sites available for that. Sure. But there will be offers. I don't want to get up here and say ours is the only thing, everything else is garbage, because that's nothing can be further from the truth. We solve a particular problem, and that solves a fairly narrow use case, but solves it very, very well. So question back here.
Sorry, this might be a little bit of a stupid question, but I think I saw the answer on that chart, but I just want to ask 2 questions. One, what is the reason that these batteries aren't at Teslas? And 2, do you think this technology is going to replace the rare earth metal technology batteries in the future?
So it won't be a Tesla because it is a liquid-based battery. You don't want that sloshing around. We have a laminar flow membrane which drives the cell, which implies that it's not being jostled. So we want to sit it down. We want to put it at a site and leave it alone. The other thing is that this is so Tesla Model S, 100 kilowatt hours? That's a small battery for us. So we're bigger than that. Lithium has a 30-year head start on getting down the commercialization cost curve. So our system is appropriate in environments where you don't want to install lithium. One of the things I didn't get into a lot was lithium has siting restrictions where you can't put lithium systems next to each other. You have to give them space. And most people here have heard of the Moss Landing fire, right? About a year ago this week, Monterey Bay lithium facility caught fire, burned for weeks. Created a huge toxic metal waste problem in the Monterey Bay. Because a lithium battery, once it catches fire, it goes out when it runs out. It's self-oxidizing. I'm off track. Next question. Right here.
What is the smallest scale that you foresee for a battery that seems to be, I guess you're saying, somewhat large and fragile inherently?
No, not fragile. What's not fragile? It just doesn't want to be in motion. It doesn't want to be in motion. A 20-foot container we expect to be a 100 kilowatt, 1 megawatt hour unit. We're targeting 10 hours of operation on our system because that's what the industry expects. You never want to fight the industry. You want to kind of, there's certain areas we have to fight the industry. We don't want to fight on all fronts. So in the battery storage world, 10 hours is the sweet spot for long duration energy storage, 8 to 14. So we sit down, 20-foot shipping container, 100 to 250 kilowatts, times 10 for megawatt for energy into hours.
Thanks. Yeah, that just be a Can you hear me?
Yes.
Topic. So at a 20-foot container, the size you're talking about, that's roughly twice the energy density of a regular or slow battery, right?
It is. Yes.
What about this chemistry or this product enables it to be twice as dense?
It's the fact that we're using bromine and hydrogen. In fact, we're using bromine. So the two competing flow battery technologies that are well understood are vanadium, which is super well understood, but it's frightfully expensive. And it's also sourced from Russia, which is another problem. Another one is zinc bromine, but it has chemical reactions that make it lower density. And the other flow battery is sodium based, which operates at stupid high temperatures and is a lot more difficult to manage. So hydrogen bromine is the sweet spot of energy density and safety. A question in the back corner.
Just kind of curious what the round trip efficiency is on this and how does that compare to other similar solutions like what you have on this chart or something like on storage? I hear right.
Well, the physics tells us that our round trip efficiency will be north of 80%. That's assuming that we bring everything together. We will have to fund our own development of gas diffusion electrodes and of the graphite plates to realize those full efficiencies. So right now we're targeting applications where the round trip efficiency is less important than the ability to store energy and deliver power. When you're in a curtailment situation where your solar energy is just getting dumped into the ground, if you can salvage 8% of it, that's a win, right? But we're going to be well north of 8. We are pre-revenue. We haven't even shipped a product to the field. So crawl, walk, run, get something out there, and then learn from that development, learn from that field experience, and then pull the levers we have to pull to push that number up. We sat down and did our product roadmap in November, and we wrote down on the left, here's all the things we need to do. And on the right, we said as measured by, and one of the as measured bys was RTE.
Do you have a sense of like how it's going to compare to some of the other solutions, like when it's at scale?
It's going to be it's going to be in the ballpark. One of the things, there's a dirty little secret in battery world, and the dirty secret is that RTE numbers are cherry picked. At a certain state of charge, at a certain level of draw, at a certain temperature, operating temperature, X, Y, Z, T, A, B, C. I had a customer who was claiming they were getting 91% round trip efficiency on a lithium. Well, the physics doesn't support that. So it was cherry picked. So we will have to publish true numbers, and that number is where we are today and where we think we can be. And those numbers will get closer over time. That's called product roadmap, product development.
All right, one more question.
Are there parts of the United States that are ideal for sourcing and then sourcing the ingredients needed to build the batteries, but then also in terms of like a manufacturing, like proximity to the source of the materials as well?
So there's a lot to unpack in that question, so I'll take them one at a time. First is the best place to get bromine in the United States is Arkansas. They have a higher concentration in the salt water at a mine there that we can extract it from because it is a byproduct of desalinization. So it's available. It's pretty straightforward. Hydrogen, you can get hydrogen anywhere. We have a specific gas diffusion electrodes, part of the reaction process. We're working with a lab in the University of Washington to refine that, and we'll probably go into production on our own 2029, 2030. And then the graphite plates, we'll probably have to own that ourselves just because of what's going on. Then for the full assembly, the balance of plant, the pumps, the tanks, the inverters, the container, the tubing, all that work, we have partnered with a Puyallup tribe up in Fife, Washington, and they'll be doing our balance of plant manufacturing. We already have that agreement in place.
Anybody else?
There was one up the front. It's a thought. Right here.
All right. Thanks all.
So obviously we all know the risks of a lithium-ion battery being ruptured, and well, this has low risk of self-ignition. What do you see the environmental knock-on effects being if somebody, I don't know, accidentally drives into one of these batteries?
So there are two risks we have to mitigate, and they're both super, super simple. First is hydrogen. We have a lot of people that say, well, hydrogen catches fire. These are not indoor batteries. These are outdoor batteries. So if you vent hydrogen to space, you vent hydrogen and it off it goes and no one cares. That's hydrogen easy. Bromine, entertainingly easy. The city of Portland is okay if we neutralize the bromine with baking soda and just dump it down the drain. If the city of Portland is good with us dumping it down the drain, I'm not worried.